Let's now take a look at derivative control. One solution to the overshoot problem is to include derivative control. Derivative control applies the brakes, slowing the control variable just before it reaches its destination. Mathematically, the contribution from the derivative control is expressed in the following equation. That is, the controller output due to derivative control is proportional to rate of change of the error signal. Figure A shows the actual and desired position of the control variable. Figure B shows the position error E. Figure C shows the derivative control output. Assume the control variable is initially set at 0. Then, at a time A, the set point moves rapidly to 30 degrees. Because of mechanical inertia, it takes time for the object to get up to speed. Notice that the position error E is increasing. It's got a positive slope during this time period A to B. Therefore, derivative control, which is proportional to error slope, will have a positive output, which gives the object a boost to help get it moving. As the control variable closes in on the set point, B to C, the position error is decreasing. That's a negative slope. So derivative feedback applies a negative force that acts like a brake, helping to slow the object. For process control systems, where the set point is usually a fixed value, derivative control helps the system respond more quickly to load changes. For example, consider a controller that maintains a constant level in a tank, a liquid level in a tank. If there is a rapid drop in liquid level, the positive slope error curve, derivative control responds by opening the inlet valve wider than proportional control alone would. Then, when the level is almost restored to the set point and the error is decreasing, negative slope error curve, derivative control helps shut off the valve. From the discussions so far, you can see that derivative control improves system performance in two ways. First, it provides an extra boost of force at the beginning of a change to promote faster action. Second, it provides for braking when the object is closing in on the new set point. This braking action not only helps reduce overshoot, but also tends to reduce steady state error. Naturally, the influence of derivative control on the system is proportional to KD in equation 11.5. Because derivative feedback improves overall system response, you might think that KD should be as high as possible. However, like so many things in life, too much of a good thing sometimes brings problems. In this case, too much derivative feedback will slow the system response and magnify any noise that may be present. What is needed is a balance between too much and too little. In the next section, we will describe methods to arrive at a numerical value for KD. It is important to note that derivative control has no influence on the accuracy of the system, just the response time, so it's never used by itself.